This is in October, November 2022, variant 41 question. Question number 3. An object is suspended from a spring that is attached to a fixed point, as shown in figure 3.1. The fixed point is here. The object oscillates vertically with simple harmonic motion about its equilibrium position. This is equilibrium position which is given. State the defining equation for simple harmonic motion, identifying the meaning of each of the symbols used to represent physical quantity. The defining equation for simple harmonic motion is A equals to minus omega squared x, where A is the acceleration, x is the displacement from the equilibrium position, and omega is the angular velocity. The minus sign in the equation tells you that F and A are measured in the opposite direction to X from the equilibrium position. That means when your F and A is acting upward, your X is measured downward from the equilibrium position. Then in part B, the variation with displacement X for the equilibrium position, the variation with displacement x from the equilibrium position of the velocity v of the object is shown in figure 3.2. This is a graph. The vertical axis represents the velocity and the horizontal axis represents the displacement. This is the velocity displacement graph. From the velocity displacement graph, we can get two very important information. The first one is the amplitude, which is here, 0.12 meter, and then we also can get the maximum velocity from here, which will be 0.2 meter per second. This is the maximum velocity. The variation with x of the potential energy, EP of the oscillations of the object is shown in figure 3.3. This is figure 3.3. This is the equilibrium position. And then this is the maximum displacement. This is a graph of energy versus displacement. From this graph, we can get two things. The maximum displacement is 0.12 meter, and also the potential energy, maximum potential energy from this point, which is 0.05 joule in the question. And then the maximum kinetic energy is this point here, red point. And then the green line represents the maximum total energy, which is a sum of the potential energy and the kinetic energy. This graph shows that the object is moving the fastest at the equilibrium position because the kinetic energy is maximum at the equilibrium position. Then at the 2 points here, where the amplitude is maximum, you find that the object is stationary. The object is stationary at the displacement of minus 0.12 and at the displacement of positive 0.12. In part 1, determine the amplitude XO of the oscillation. You can get answer either from figure 3.2 or figure 3.3. The answer is 0.12 meter. And then in part 2, show that the angular frequency is 1.7 radian per second. There are two ways to get this answer. Both the answer come from figure 3.2. We can use Vmax equals to XO times omega. The velocity maximum is 0.2. The XO is the amplitude, which is 0.12. Then omega equals to 0.2 divided by 0.12, which is 1.7 radian per second to 1 decimal point. Another way to do the question is to get the green point here. At the green point, the coordinate is 0.08 for displacement and 0.15 for the velocity. So we use velocity equals to omega square root of amplitude square minus x square. This will give you omega equals to 0.15 divided by square root of 0.12 square minus 0.08 square, which will give you 1.7 radian per second up to 1 decimal point. Then in part 3, we have to determine the mass of the object. From figure 3.3, we find that the E total maximum is equals to the total maximum kinetic energy, which is also equals to the maximum potential energy. The formula for maximum potential energy, the formula for maximum kinetic energy is half m omega square xo square. This will give you 2.49 kilogram. Or you can use this equation directly to get the answer, which is 2.5 kilogram. In this part, the oscillations of the object is now lightly damped. What is part 1? State what is meant by damping. Damping is a loss of total energy of the vibrating system due to some resistive forces. This will get the 2 marks. And then in part 2, assume that the damping does not change the angular frequency of the oscillation. It means omega stays the same. On figure 3.2, sketch the variation with x of velocity when the amplitude of the oscillation is 0.06 meter. We have to use the equation Vmax equals to XO omega. Since omega is a constant, we can say that Vmax is proportional to amplitude. Therefore, we can write 2 equations. This equation is for the amplitude of 0.12. So 0.2 equals to 0.12 omega. This is the first equation. Then the new velocity, which we don't know, is equals to 0.06 because the amplitude now is 0.06 meter times omega, since omega is a constant. Second equation. Then you take equation 2 minus equation 2 divided by equation 1, you get V divided by 0.2 equals to half. So V equals to 0.1 meter per second. That means the graph will be like this. This is a graph. When the amplitude is 0.06, the maximum velocity is 0.1 meter per second. This is a summary of the facts that you need to know to solve this question. Number 1, we need to know the defining equation for simple harmonic motion. And then we must be able to identify the meaning of each symbol used. For example, the defining equation is A equals to minus omega square x. Number 2, you must understand the velocity displacement graph and know that you can get amplitude and the maximum velocity from this graph. Number 3, understand the energy displacement graph and know that you can get the amplitude and the maximum total energy, which is the sum of the kinetic energy and the potential energy, which is equals to the maximum potential energy, which is also equals to the maximum kinetic energy from the graph. Then number 4, you need to know the equation that Vmax equals to XO amplitude times omega. And the maximum total energy is the same as the maximum potential energy, same as the maximum kinetic energy, which is equals to half m omega square xo square. This is a formula for the maximum kinetic energy. Then finally, you must understand the term damping.